Okay. So these are the notes for vertical shifts on rational functions. We've talked about all of the key features of a rational function at this point, which would include your horizontal asymptotes, your vertical asymptotes. We've talked about our x and our y intercepts. And from here, the last thing that we can do is we can then say, well, what happens if I find all that stuff, but I move it up a certain amount of number? So let's review graphing the following features that we just discussed for this guy right here. So I'm gonna try, there we go, to see if I can graph this. Use a different pen. So our vertical asymptotes will be when the denominator equals 0. So 2x squared minus 8. I'm going to shift my 8 over to the other side. 4, when I divide the 2 out, square root, and I'm going to get x equals plus or minus 2. So something's going to be happening at plus or minus 2. So if I put in plus or minus 2, I'll do it right here, f of 2 will be 8 over 0, and f of negative 2 will be negative 8 over 0. So that means that we have asymptotes in both cases, not holes. We've got those two vertical asymptotes. Then we're going to go to horizontal asymptotes. And we'll put our dominant term over dominant term, and the denominator is going to grow faster. So small over big means we're going to go to 0. So again, we plot what it isn't before we plot what it is. So let's do our x-intercept, which will be when y equals 0. And our y-intercept will be when x equals 0. So this one will be, if we plug in 0, so f of 0 is 4 times 0 over 2 times 0 plus 8, so we're getting 0 over a number, so 0. So this is the point 0, 0. And our x-intercept, 0 equals, let's see, I'll do it right here. 0 equals 4x over 2x squared minus 8. I multiply both sides through by the denominator. Look at 0 equals 4x on this side, so divide through by 4, and we would get x equals 0. So we only have one intercept here. It's the x-intercept is the y-intercept, and the y-intercept is the x-intercept. So that's good. So now we need to figure out what's going on from the left and the right towards each function. So let's see, let's go towards the limit as x approaches 2 from the right, and then we'll do it also from the left. So when we do it from the right, we're going to get, let's see, basically 8 over, let's do 2.01, and I'm going to show you guys a cool trick for those of you who have these kinds of things. We're going to go to our home screen and we're going to go to graph, and then we're going to delete all this, and I'm going to input my function 4x divided by the quantity 2x squared minus 8, and we got to take note, F1, enter. So it graphs a rational function. Yes, that's nice, but if it didn't graph it for us, we could go to our home screen and calculate. So I'm going to do variable F1, and I want to go 2.001. So that's a really big number. So a number that's slightly greater than 2, which would be this from the right, is going to go to, so this must be a small then, going to go to positive infinity. Okay, and then heading off this way. From the left, a number that's slightly smaller than 2 would be plugging in to our function that we defined, 1.999. Ooh, and it's going down this way. We're going to do the same thing for, this is going to go to negative infinity. The limit towards -2 from the right and left. I'm just going to use my calculator again. F1 to the right of -2 would be -1.99. It's close enough. Getting really big on this side, so whoop, that way. And then same thing, and to the left will be -2.001. That guy's going down. Then off this way. Now if I had to do that all by hand with an old-fashioned calculator, I could, but for now I'm going to do it that way because it's faster. So that's a review of everything we would need to do to graph a rational function. So those are the 3 pieces of this one function. So let's extend. Let's take this same function and we're going to add 3 to it. So a vertical shift means that for every x, y point we have, so if I had x, y initially, when I add 3 to it, I'm gonna, whoop, I didn't want to do that. Let's see if this fixes. There we go, the perks of working with cheap equipment. So x, comma, y is 3 further up than it was. So whatever it was, it's now 3 further up. So let's choose some points. Let's say this point right here, and then this horizontal asymptote. So these are really the only things that are going to be dramatically shifted. So our horizontal asymptote was at 0, so now it's at 3. Our vertical asymptotes are not going to change. The value that makes the denominators equal 0, nothing has been changed. So we're still doing this. Still doing this on this side. This point right here used to be at 0, 0, but now it's going to be 3 further up than it was. So now it's at 0, 3. So we're looking at basically the same thing. This guy's going to shift now towards the right and go down. This guy going to go up as it goes to the left. We still have this shape going on here, and we still have this shape going on here. If we wanted to, we could make it a little bit more precise by figuring out exactly where this and this are going to go across the x-axis, which means that x-axis is y equals 0, so I could do 0 equals 4x over 2x squared minus 8 plus 3, so -3 and then you would multiply through, and then you would have a horrible little quadratic to solve. So if you solve this, you will get 2 values, okay, and those values give you these. Solve this, get these. But I'm not going to be super picky about that for this moment. I just want you to learn that shifting it up and creating that same shape is enough to get you to go. So review of vertical shifts from previous things we've looked at. If I had my parent function that looked like this, my shifted would be 3 up, This point right here will be 3 up. This point right here will be 3 up. Oop, doesn't look very symmetrical, but it will be. So something like that. Okay. 2x plus 4. It used to be something that had a slope of up 2 over 1, down 2 back 1. But now every point is 3 further than it was. So should be parallel, but 3 up. Oh no, oh no! Pretend that this is a 3. I really love that. Okay, so pretend that this is a 3, not a 4. Sorry about that, guys. Here's another one with a vertical shift of 3. If, by the way, if this had been 4, it just would have been that everything was 4 further up than it was. 2 to the x. If I plug in 0 into this, I'm going to get 0, 1. And if I plug 1 in, I'm going to get 2 to the 1, which is 2. And then if I plugged in something really big and negative, so like 2 to the negative 1,000 or 100, would be pretty darn close to 0. And then if I plug in something big like 12 even or 10, we're already getting huge really fast. So it's going to go up really fast, hence exponential growth. Okay, and then we've got a horizontal asymptote. Oh my gosh. Horizontal asymptote at 0. So if I shift everything up 3, my horizontal asymptote is now at 3. My y-intercept is now at 4, and this point 1, 2 is now at 1, 5. So it's going to do this kind of thing. Okay, and that's what shifts on rational functions up here look like. And then here is a review of vertical shifts on other types of parent functions. So quadratics, linear, and exponential as review. See you in class.